Hey guys, today we are talking about Faraday's law and Lenz's law. But for today, we are mainly discussing the possibility that a change in EMF or current can cause a change in magnetic field. Today we're talking about the reverse, which is how the change in magnetic field can induce a current or create an EMF. So without further ado, let's look at the actual equation. The Faraday's and Lenz's law is EMF equals to, and this is very important, negative the change in magnetic flux over the change in time. Both Lenz and Faraday contributed to this equation, and the Lenz contribution is very important negative sign, and the rest is come up with Faraday's. The negative sign has to do with the principle of the system, that is, the system does not like change. Whenever a change occurs in the magnetic field, the system tries to think of a way to bring the field back to the original state. So a current is induced to try to reduce the change in magnetic field by creating a magnetic field opposite direction of the change. Now, let's look at an example demonstrating how we can find the direction of the induced current. Over here, we have a magnetic field shooting out of the page, like demonstrated here, in an increasing magnitude, and we wonder what is the direction of the induced current. Here's another angle of the magnetic field, and since the system does not like change and the field is trying to increase outward, the induced current must create a magnetic field that directs inward like this and try to bring back the magnetic field to the original state. Therefore, we can use the right-hand rule, thumb points into the page, and boom, here is the direction of the induced current, clockwise. Let's look at another Faraday's law problem. In this kind of problem, it's called motion and EMF problem. It usually involves a metal bar or some kind of conductor moving a magnetic field. In this case, we are given that the magnetic field is pointing inwards, the direction of the magnetic field. We are also given the magnitude, which is 0.5t. We are also given that this slider that the metal bar is sliding on is all conductor, thus it will be a current that runs through and across this circuit. And the resistance of such circuit is 1 ohm. Let's make the problem simple. And then the metal bar itself is moving to the right with a velocity given here, 2 meters per second. And what we are wondering is the current that runs through this circuit, what is the magnitude of direction of this induced current? And also, if this bar is has to move in constant speed to the right, what kind of force should we apply on the metal bar to keep it moving in constant speed? I'll encourage you guys to pause here for a second to think about this problem on your own, and then we can talk about the problem afterwards. Okay, I believe you guys have already looked at the problem. Some of you might wonder, there is no V mentioned in the Faraday's law whatsoever, so why do we need that value? Don't worry about it right now, let's look at it together. First of all, let's write down the Faraday and Lenz's law to start with. EMF equals to negative the change in flux over the change in time. Okay, at this point, we need to do something to the magnetic flux to kind of include the value of velocity in there. Some of you might recall magnetic flux basically equals to B times A over delta T. And in this problem, we are also given that the metal bar has a length of L. And for each moment, the metal bar moves to the right with a distance of dx, so that we can rewrite the area as L dx over dt. Okay, so here we can see that there's something familiar coming up here. dx dt, isn't that just v, our given value? Yes, so that we can substitute it in So we get B, which is a constant, so we can take it out, and L, which is also a constant, times V, which is a given value. And then we plug in all the numerical value we are given, and ta-da! Oh, I just realized I forgot to give L in value. Okay. So for the purpose of this question, let's give L a value of 0.1 meters. Okay. So now we can actually plug in the number and get, as we see, B equals to 0.5 times L 0.1 times V 2 meters per second. So then we get the mth as 0.1. However, this problem asks for the magnitude of I. So let's make a basic conversion. I equals to mth over resistance, which is 1 ohm. So 0.1 over 1 equals to 0.1A. Yay! Did you get that? Let's do part 2 of question 8, which is, what is the direction? Let's think about it. First, according to Lenz's law, which is the negative sign in the equation, the negative sign means the current should produce a magnetic field that's opposite to the direction. Therefore, the current should produce the magnetic field that's pointing out of the page. Okay, since the magnetic field is pointing out, therefore we use the right-hand rule, thumbs up, and here is the direction of the current, which is counterclockwise. What is the force applied that keep this bar moving in constant speed? Let's think about this. In order for the bar to move in constant speed, the net force has to equal to 0. So let's think about what force there is in the system. First of all, there must be a force exerted by the original magnetic field, F mag, and there should be another force that's going into this direction, F applied, which is what the question is asking for. Therefore, we can set them equate to each other's opposite, like this. Okay, let's think about how do we calculate this force. So the magnetic force, as we recall, can be calculated by magnetic force equals to I times L cross B. In this case, since L and B are perpendicular to each other, so we can ignore the cross sign. And then we plug in the values. I remember is 0.1 m times L, which is 0.1 meter, times B, which is 0.5 t. This equals to 0.0005 newtons, equals to F applied. So here we go. This is the answer to this problem. Let's look at another application problem, which is probably another aspect of the... Okay, here comes the challenging problem. I pulled it out of the MIT problem set, so if you finish this problem, you can officially do MIT problems. Yay! Okay, the given in this question is that this rectangle loop of dimension L times W moves in a constant velocity away from a long straight wire that has a current in this direction in the plane of the loop. And the question A is a good old Ampere's law problem. Let's find the magnetic field at a distance s away from the straight current carrying wire. Let's pause for a second and try to do this problem. For those of you who don't remember, flip through your notes quickly and find the equation. Okay, so let's look at the problem together. If you remember Ampere's law, it's that the integral of b times ds equals to mu naught times I through. First of all, we have to figure out what is the integral of b times ds. As you recall, we can draw, assume this distance is s, we can draw a kind of loop around, which is the same distance ds from the wire. Since b and ds are perpendicular, we can simply rewrite it as that b times the perimeter of this circle, which is 2 pi s, equals to mu naught times I. Now we can simply see that the magnetic field equals to mu naught times I, which in this case is I, over 2 pi s. A straightforward Ampere's law question. For problem B, what is the magnetic flux through the rectangular loop in an instant when the lower side with length L at a distance r away from the straight current carrying wire? This is also a review problem. The equation for magnetic flux equals to the closed interval of B times dA. Since the loop is from here to here, we plug in the magnetic field here, and then we integrate the whole thing, and boom. Since we have to integrate the s, we can change dr into ds. They're the same thing since they both represent distance. And then we pull out all the constant, of course, these little things, and we're left with this. Oh, and L here. Now is your test your calculus skill part. Ln, our old friend Ln, equals to r plus w minus ln r, which can be transformed as r plus w over r. And here we go. This is the equation for our magnetic flux. Okay, now let's proceed to problem C that I didn't show you guys yet. As you probably recall, each thin strip here with the width of dr has the same magnetic field. Therefore, if we're integrating from here to here. And the area of this thin strip is dr times the width, which is L. And what about the two side, the limit? Here we can see the R here is the lower side of the limit, and the upper side of the limit, you can see it's W plus this distance, which is R plus W. And now we can integrate this area and find that the magnetic flux equals to. Okay, let's look at the problem C, which is actually the problem specifically focused on the Faraday's law. First of all, I feel like I forgot a part in problem A, which is the direction of the induced magnetic field. Let's figure out together here. First of all, we know the direction of the current is here. Using right-hand rule, thumb points the direction of the current, and we can find out that the magnetic field inside the loop is in. Okay. Let's think about the direction of the induced magnetic field should be. Since this is very important, this is moving away from the wire. And if we look at the equation here, if S increases, the whole B decreases, which means it is decreasing in the direction in. That means the loop should create a magnetic field that's reinforcing this magnetic field, since it does not like change. So therefore, in order to create this inward magnetic field, the direction of the induced current should, let's use the right-hand rule, thumb points in, and we can figure out that it is actually going to induce a clockwise current. Okay, now let's get into the actual magnitude of such nth current. First of all, we know that current equals to mth over r, so what we have to figure out is the mth. To figure out the mth, we are using our old friend Faraday's law. Mth equals to negative, almost forgot about that, change in flux over the change in time. The flux equation we already get, so we only need to take the derivative of that over delta t. Now we need to use a little bit of calculus skill here. Taking this derivative is kind of tricky. Basically, I'm going to just write out a constant first, times, since it's the derivative of ln, which is basically the reciprocal of r plus w, times the reciprocal of 1 over r plus w, which is r, times derivative of r plus w over r, which we'll figure out this whole thing equals to w over r squared and negative. Oh, it's a little bit messy here. Let's move it down here. Yeah. So this whole thing, I'll try to make this legible, I promise. Equals to r over r plus w times negative w over r squared times dr dt, since we're taking the derivative, as you guys remember. And dr dt, we know that this equals to v again, so the final equation we get is not negative mu naught il over 2 pi s times r plus w. This two cancel that one, so it's r times v w. Here we go, a little bit messy. Now let's look at the equation for I, which is fairly simple since there isn't much more derivative to take and stuff. Okay, here we go. So I equals to mth over r, which is this whole mess, times 1 over r. Finally, here we go. The real equation for the current. And don't forget, it is a clockwise current. Here are all the problems and concepts I'm going to talk about. Thank you for watching, and I hope you enjoyed this video. If you have any problem, ask Mr. Kerrigan or do more problems. That is good for you. Thank you.